I want to thank the organizers for setting up this great conference and also thank them for inviting me. So my talk will mainly be about a paper from last year that we called Will It Glue? And it's actually a nice collaboration with these people you can see here. So with Lorenzo Jonas from CWI in Amsterdam, with Jonas Haferkamp from Bochum soon, and myself from Berlin, Tommy Schuster from Caltech, and Soltan Zimboras from Helsinki. And since the scope of this workshop is a bit broader, I thought it would be also a very good opportunity to briefly recap, what happened in the theory of random unitaries in the last 2 years, which was quite a lot. So I hope you get something away from that. So maybe let's start a bit and motivate why we are looking at random unitaries. So these things actually have become like a major tool in quantum information theory. So they pop up in all different places. So I'm pretty sure that a lot of you already saw like a random unitary in one or the other setting. So there is, of course, there are like quantum advantage experiments, namely what Google did, random circuit sampling. There's boson sampling. Then there is quantum learning settings. So both in the theory of quantum learning as well as in practical protocols like randomized measurements or shadows. These play a large role, and they're also very important for cryptographic primitives. There has been like a lot of work on pseudo-random states, pseudo-random unitaries, and they're also very useful for characterizing quantum devices. So learning about noise, learning about we heard this from Jadwiga, like learning about basically characteristics of noise. And there's like very famously randomized benchmarking as a protocol that uses random unitaries. And they also serve as toy models in many-body physics. So they really like to study quantum chaotic behavior in random circuits. And they also pop up as a model for scrambling on black holes. So just to get everyone on the same page, so the gold standard for random unitaries are Haar random unitaries. So where we resemble these things from the Haar measure onto unitary group. So the Haar measure can be thought as like being like the most uniform measure on this group. So what we require is that the measure is invariant under multiplication with unitaries. So this can be seen as like translations on the group. And we want that basically, the measure is invariant under translation, so it's uniform. By the way, this works not only for the unitary group, but actually for any compact group that you want, and in particular for subgroups of the unitary group. But the big problem here is that Haar random unitaries generally have exponential circuit depth. So we cannot really do them. So we're looking for alternatives, something that is like weaker but still strong enough for what we want to do. And this leads us naturally to the notion of designs. So a K-design is basically an ensemble of unitaries. And what we require from this ensemble is that if we create the ensemble K times, so we can basically take K unitaries from this ensemble, and we can do anything in between. So we can use ancillas, we can do like adaptive operations. That basically we not be able to distinguish this from a Haar random unitary with only K queries. That's what a K-design is about. There are slightly different notions, or not slightly, but there are different notions of designs, and we'll talk a bit about this later, but for now, that's what we want to work with. And there's a classic result that I can generate such designs from random circuits. So if I take a circuit made of local gates and I arrange them like in this like famous brickwork fashion here, then if I make this circuit deep enough, this will become a K-design. And deep here means that I take the depth to be linear in the number of qubits and linear in the number of copies I want to have. So this is like, has been established in the literature, like, and subsequently proved by these papers down here. But it's kind of interesting to see that not all statistical features actually converge at the same rate. So we have this like, so this can be seen as like basically a worst case depth, but there are certain things that converge much faster. For instance, there's anti-concentration, which is basically we're looking at the outcome distributions of our circuit. So we look at the final state, measure it on the computational basis, we look at the distribution, and in expectation, this will be flat. So it will be uniform. And what we're interested in is like how these things actually fluctuate around this expectation value. And if these fluctuations are of the same order as the expectation value, so 2 to the minus n, then we say this anti-concentrates. And we can measure this by looking at the, so to say, the second moment. So we could look at the variance of these fluctuations. And so we calculate the second moment. And we can see this as basically taking the circuit twice and contracting it with like 0 states and then taking the average. And in 22, it was proven that this actually converges already in logarithmic depth. So exponentially faster than we would expect from the worst case. And in hindsight, this could have been like a nice indicator that there is like actually like a very interesting regime at log depth. Namely, the definition that I just gave you here, we don't need deep circuits for that. And this was a result from 24 by Tommy Schuster, Jonas Haferan, Robert Huang, and a parallel paper by Nicola Rokente and Felix Uditsky that showed that actually we don't need to take deep circuits, but actually only logarithmic depth circuits. And you will not be able to tell this apart from random using experiments that look like this. And this is kind of surprising, because I mean, linear depth kind of makes sense because, light cones. And if you have like, logarithmic depth circuits, the light cones will just be like super small. The final state will be not entangled in any meaningful way. And so this actually, I had a lot of discussions with many physicists about this. They were puzzled because, but the resolution is that you cannot probe light cones by experiments like this. So what you actually need to probe light cones are inverses. So, so we will get back to this a bit later, but I think it's kind of like, it's really nice to see how this proof works, because it's actually pretty simple. And it works by construction that they call cluing. So if you take a lot of small K designs, and then we can clue them together if their overlap is sufficiently large. So, and sufficiently large here means that they have to overlap on a logarithmic number of qubits. And these things then actually clue together and form a big K design with a very small error. And if you have this, like, if you have such a cluing lemma, then you can immediately get logarithmic depth constructions, because you can now just insert the linear depth results that you know from before for every of these small K designs. And because the small K designs only act on logarithmic size patches, linear depth means that they are also only logarithmic depth. So these are basically log times log kind of circuits. And now I take 2 layers of that, and then again a log circuit. So this is kind of nice. So from such a cluing lemma, you automatically get these like log depth constructions for free. But I also told you, like in hindsight, you could have seen this from anti-concentration. That's actually what we showed in a paper from last year, that at least if you look at 2 copies, you actually get 2 designs from like anti-concentration arguments already. Okay. But clearly, in logarithmic depth, you cannot do everything, right? So there's like, don't have full light counts. You cannot really create much entanglement. So where's the catch? As I indicated before, the difference lies in what kind of experiments you allow to probe your random unitaries or your random ensemble. It's actually very fruitful to think about this, like basically as kind of like an adversary that tries to, prove that this is not random. And so if you allow the adversary to only probe U K times, you will not be able to tell apart log depth circuits from random, as I told you. But if you allow the adversary to also probe U dagger or U complex conjugate or transpose, then you need linear depth circuits to be secure against such an adversary. And this is actually was also a paper from last year down here. And so somehow, like this, crypto style perspective, it turns out to be very fruitful in the analysis of random unitaries. The reason for that is again, as I said, if you have like light inverses, I can make light cones appear, and then I can test whether my circuit is sublinear or linear. But actually, is this like somehow like a general phenomenon? Like, is this like, or is it like very special to the unitary group? But that's what we did is actually we looked at restricted circuits, so like circuits where the gates come from like some subgroups, and then we ask like whether such subgroup designs actually clue. If they clue, we get logarithmic depth constructions. If they don't clue, then we actually were able to prove linear lower bounds. So basically, yeah. And let me just illustrate how this works. I also wanted to mention, sorry, that there's also like a parallel paper by the Los Alamos gang and Martin over there. They basically proved the same stuff as we did. So a nice example is the orthogonal group. So we just take like real unitaries. And the important bit here is that the two-copy action of the orthogonal group has an invariant state, the maximum entangled state. And a nice feature about the maximum entangled state is that it factorizes over the qubits. And now we can actually exploit this. So like let's consider a local circuit made from orthogonal gates, 2 copies of it, and we let it act on these like copies of the maximum entangled state. But for this to be non-trivial, we have to introduce like some small perturbation. So we add like a local set gate, for instance, on the first qubit there, such that the gates not vanish. But what's now happening is that basically all the gates which are not in the light cone of the first qubit vanish because they act layer by layer on this maximally entangled state and basically kill themselves. And so we now made a light cone appear. And we can now test for this light cone because the lower part of the system is not entangled with the upper part of the system. So formally, what we can do is we can design a test that looks a bit like follows. We select a random qubit, and then we measure the maximum entangled state on that qubit. Or it's actually 2 qubits, but and we get a probability pi. Yeah. And then now let's assume that the light cone is actually not all qubits, but just a fraction of it. Yeah. And then the probability that we've selected like a qubit that is not in the light cone is 1 minus alpha. And so we can then lower bound the expectation over these PIs by 1 minus alpha times the probability of measuring on the IF qubit, which is 1. Because if I'm not in the light cone, I'm down here somewhere, and I just get like basically the overlap of the maximum entangled state with itself, which is 1. And this gives a lower bound on the expectation value. But in the higher case, we actually get like something that is exponentially small. So we can tell these 2 scenarios apart if, for instance, like alpha is like 1/2 or so. Yeah. And it's easy to tell them apart. And this kind of like logic generalizes very well to other groups. So basically what we're looking for are invariants of a group. So these are like operators Q that commute with the K copy action of my group. And we want that these operators factorize over the qubits such that we can do this nice trick that I just showed. And we also want that these things are positive semi-definite. So these are operators where the eigenvalues lie between 0 and 1. And then what we can do is now we can like arrange these operators in the middle, and now we have basically U dagger acting from left and right. And we again introduce this perturbation on the first qubit to make a nice light cone appear, because now basically all of the gates again like they act on the Q in the middle, and this action will be trivial, and then the next layer acts, and the next layer acts, and then we get this like light cone here. And then now we can again do a test. We can just select a random qubit. We can measure the IF operator there, and then we get basically by the same logic as before, we get the lower bound on this expectation value. And this is so if the H value is sufficiently small, then I can again tell these things apart. Yeah? But let's say for a general group, I cannot really compute this value. So let's just look at some examples. And what we did was basically we looked at the orthogonal group, the unitary symplectic group, the Clifford group, and the match gate group. And in all of these cases, this is like gives us like an efficient test for sublinear circuits. Okay, But to be fair, this only works in 1D. Yeah? So this is like a light cone argument, so it depends on the architecture, and we get these linear lower bounds only in 1D. In all, for instance, we get log lower bounds, and so on. So they are, in this sense, they are a bit, well, I think they're not weak, but it depends on the architecture. Yeah. But what we also did is we also constructed architecture independent lower bounds. But this only works if we go to like a slightly stronger notion of designs. And the stronger notion of designs are so-called relative error designs. And here we are not talking about discrimination, but we talk about reproducing outcome probabilities of such circuits with a relative error. So we look at basically some arbitrary input state. We do like the k-copy action of my circuit, and then I project onto some outcome. Huh? And I want that these things are reproduced with relative error. This is quite a strong requirement because these things can be exponentially small. Nevertheless, in a unitary case, you get relative error designs in logarithmic depth. Okay, so how does the argument go? We look again at this invariant Q, and now we introduce this like perturbation on the very first qubit, the set perturbation. And the thing in the middle now is basically the input state row. Because Q was PSD, we can basically interpret this thing in the middle as a state. And then we act with the k-copy circuit on it. And now what we can do is we can just conjugate the Q in the middle with U dagger. And this will kill basically all copies of U except one. So we basically, we now get equally this expression where now the set operator is conjugated. And this is something that's very well known in the literature. It's called Pauli scrambling. So we look at basically how fast does like this like local operator spread over the circuit. And generally, this is not too fast. It needs like linear time. And this is why the argument works, because you now can basically relate outcome probabilities, convergence of outcome probabilities to convergence of Pauli scrambling. And to see why this works, let's go again back to this picture. So we have now like the red thing is now the set operator on the first qubit. We have our local circuit acting on it from left and right. And just for the sake of the argument, let's say we have Cliffords. Then we can now look at the action of the very first 2-qubit gate on this set operator. And then there's a certain probability that the outcome, so the image of this set 1 operator, is again weight 1. So we have like 15 possible Paulis that could come out, and 6 of them have weight 1. So the probability of getting a weight 1 operator is after the first layer is 6/15. And now we can repeat this for the second layer. It's again a weight 1 operator, and I can ask like how high is the probability to get another weight 1 operator? And it will again be at least 6/15. And now I can iterate this after L layers. I have like 6/15 to the L as a lower bound for my probability to have a weight 1 operator in the end. But basically from a hard calculation, what we expect is something that is exponentially small. So if these things should be like within relative error of each other, then the number of layers has to scale linearly with the number of qubits. So that's essentially the argument here. It also works for basically also works for orthogonal and symplectic because it essentially always boils down to a 2-copy calculation. And if I take the orthogonal Cliffords, there are 2 designed for the orthogonal group, and if I take the symplectic Cliffords, there are 2 designed for the symplectic group. So I can always basically retreat to this discrete case where I have Cliffords, and I can simply count things. Okay. Actually, we also have some other results. So like basically now I talk to you when it doesn't clue. Now it sometimes also clues. Yeah. So but to make this happen, we have to adapt like a weaker notion of design. So for these like strong ones that I just told you about, things don't clue. But if you look at these like additive error state designs, then it clues. And so let me tell you what the additive error state design is. So here, the idea is that instead of telling apart unitaries, what we want to tell apart are states. So we have basically we can now see as our circuits to generate a state ensemble. We take k copies of our circuit, we let it act on the k copies of the zero state, and this will give us a state ensemble. And if you cannot tell apart this state ensemble from high random states, then we call this like a state design or additive error state design. Okay, and what we were able to show was that that we can actually, for at least for the orthogonal and the symplectic group, for such state designs, we can basically exchange the average over our group with the unitary average. So with the average of the unitary group. And so this basically, formally, we look at k-copy action onto some state, and we require that this state has a positive partial transpose over the copies. Yeah, so the zero state certainly has a positive partial transpose, but we will also require this like for bit more general states later. And then we can basically exchange this average over, say, the orthogonal group with an average over the unitary group, and we get some error. And now let's see how this works for cluing. So we have basically two small designs here over our, let's say, the orthogonal group. We can now exchange the first layer for an average over the unitary group because zero is PPT. So we can get a small error there. But now we can actually also do it for the second layer because the output of the first layer is actually a convex combination of product states. So we can now exchange both layers for averages over the unitary group. Then we can use the unitary group cluing lemma. So we get a big unitary average over unitaries. And now we can basically use this PPT lemma again, like but in reverse. And we picked up like some additive errors on the way, but the one that is actually dominant is the one in the last step. And so this kind of construction gives us errors that are larger than some poly k to the minus n. But orthogonal doesn't, no? Yeah. No, yeah. It also works for the Clifford group, for instance, but only if k is 4 or 5. But some other people proved it for higher k, actually, but not with this kind of technique. Yeah, okay. You can ask again in a second. No worries. So here's like a short summary of our results. It's kind of like, I arranged it in a table because we have like, different groups. We have the orthogonal group, the symplectic group, Clifford, and matchgate. And we have these different notions of designs that I've talked about. We also looked at anti-concentration. And then we have basically these like different, no means that we have linear lower bounds, and yes means we have logarithmic upper bounds. And like the thick line is basically indicating our results. Okay, so let me give you a brief outlook. So I think what's nice about this paper is that it shows that subgroup designs behave very differently from unitary designs. So like intuition doesn't really carry over. So because these invariants allow to simulate light cones, adding inverses to the whole thing doesn't really add much. So we have to look at basically, the barrier between like log depth and linear depth is somewhere else, and we have to basically study like a more fine-grained picture to look at these different convergence regimes. Subgroups can also arise through symmetries. So this is something that many people are very interested in. There's like some papers on energy conservation and on-site symmetries, and I think like they also fit nicely in this framework. And last thing is like I think that it also gives a new perspective on doping. So this is basically this idea that you have a Clifford circuit and you add some T gates to it. So this will converge to a universal circuit, and the question is like how much T gates do you need to for instance, generate a design? And we looked at this in the past, but I think that basically our results somehow indicate there is like a more fine-grained picture on the use of magic resources for scrambling. Okay, with that, I want to thank you and advertise that if you're interested in random circuits, we have this workshop in August, and yeah, feel free to talk to me about it. Thank you very much.
So thanks, Max, for the talk. Are there questions? Not at the moment. Oh.
Cool talk, Markus. One question for maybe the old people like me. If you look at the geometry of minimal state designs, kind of like, can you learn something new about maybe SIG PVMs or things like this? Kind of like really look at kind of like, you now can generate very, very small state designs, right? Because the circuits are only log depth.
Yes.
What do these look like? And can you kind of like learn something about such minimal geometries on the block sphere?
That's a good question. I haven't really thought about it. The one thing is like somehow this minimality is typically for exact designs. And here we're talking about approximate designs. I know that there was like some recent paper that kind of like tried to, so they have this like Welch bounds, and I think they tried to generalize this to approximate designs. But so I'm not so sure. Like, okay, I don't really know. So, yeah.
Okay, I have a question from someone from outside the field, because you talked a lot about the gluing operation with diagrams.
Yeah.
But could you define it a bit better? Is it that you sample from both sets? Or?
Yeah. So you sample independently. So I don't know. So basically, you have all of these blocks, and they're all independent. So they're like basically like gates. So you can you sample from all of these like independently, and then basically on average, this will give you something that looks like a big, like a sample from like a big design, so to say.
So from a bigger pool. So
no, just a design on a larger system.
Okay.
Because you have this. Okay. It's basically up there, no, like in the corner. So you have basically this like they act on like some subsystems, both of them. So basically there's like one acts on AB, then one on BC, and the thing glue together to like a design which is on ABC. Yeah. And the error here in the weakly lines, they depends on the size of the subsystem B. Yeah.
Any more questions? Okay, then if not, let's thank Markus again.